And that is an important thing to remember because, and consider, because what we're going to do next, and this is where we're getting into the latter part of chapter 9, but we're going to be getting into some things in chapter 10 as well. Because when you connect a resistor and a capacitor, not to a battery, but to an alternating current, an alternating source, an alternating sinusoidal source, we're going to find that the voltage waveform and the current waveform, in fact, are out of phase across the capacitor by 90 degrees. So, can I erase this, some of that? I want to take a picture of it first. So I'll just erase this part here. So if we take that source and replace that with a alternating current source, an alternating power source, I keep saying current. What's going to happen is that, and we put in a meter to measure voltage and a meter to measure current. What we're going to find out is that we're just going to say that voltage is the reference. So I'm going to draw that at 0. We're going to find that the current is out of phase with the voltage by 90 degrees. And actually, in order for it to be out of phase by 90, we got to get rid of that resistor. We're going to start out with a simple circuit, just a capacitor. So the current waveform is going to look like this. Oh, well, that's not so good. But this is 90 degrees here. So when the voltage is 0, when the voltage hits 90 degrees here, the current is at 0. When the voltage is at 0, the current's at a negative maximum, and this is 90 degrees here. And I'm going to put this as, since I used angles, I'm going to put that as theta. Now let me just make sure I drew that correctly, because okay, I think that's right. So if the voltage is this, the current is this. Current leads voltage by 90 degrees. And the one way to represent that, to remember that, is to think of the word ICE, I-C-E. There's the capacitor. This is the symbol for current. This is not the symbol for voltage. The symbol is V, but years ago it used to be, voltage used to be called electromotive force, and in a lot of places it's stuck. So current, for the purposes of this memory device, when you have a capacitor, the current leads the voltage. Always, always, always. Current leads voltage. When we get to inductors, we're going to have another memory device that will, I'll show you, I'll show it to you now, but I'll introduce it later as well. When you have an inductor, the symbol for an inductor is L, and in an inductor, voltage always leads the current. So when I was in school, my professor always said, just drilled it into our heads, just remember the sentence, Eli the Iceman. Eli the, no, all right? Eli the Iceman. And of course that goes back from the 1930s, 1940s, when refrigerators didn't exist. They had ice boxes where ice was delivered by the Iceman, and that's how you kept your food cold. And at the time that I was in school, there were people that still remembered that. Today it's not something that people think of, but the memory device is still in place. So for a capacitor, current leads voltage by 90 degrees, always by 90. Now when we introduce a resistor into the mix, the current will lead the voltage across the capacitor, but it will not lead, the current will not lead the voltage across the resistor. It'll be in phase with the current voltage will be in phase. So the overall, the net effect will be something less than 90. Well, we're going to get into that. Okay, who has questions so far? No questions? So obviously when you connect a capacitor to an alternating source, a sinusoidal source, there's going to be a certain amount of opposition to the flow of current. I mean, these things are not perfect devices. And the opposition that a capacitor offers to the flow of a sinusoidal source is called capacitive reactance. And the formula for capacitive reactance is a function of frequency, and it's a function of the size of the capacitor. The symbol for capacitive reactance is X sub C, and the formula is 1 over 2 pi times the frequency times the capacitance. And that value is ohms. Resistance is in ohms, capacitive reactance is in ohms. When we study inductors, we're going to be looking at inductive reactance, that's in ohms, and the combined effect of resistors and inductors and capacitors in a circuit is called impedance, and that's in ohms. Everything's in ohms. All right, 1 over 2 pi FC. Now think about this. It's a kind of an inverse relationship, and it depends on frequency. Let's just say your capacitor is fixed. So if your waveform is in the positive cycle, you have one side of the plates, one side of the plate going positive, the other side going negative. And just when this thing gets charged up, what happens? Whammo. The AC wave switches and it goes the other direction. So now the positive plate is starting to go negative, and the negative plate is starting to go positive. So you have this back and forth. And even though that capacitor is an open circuit, and there's a void between the two, it actually conducts electricity quite well because of the fact that it's connected to an AC source. The faster, and remember, as soon as you, in this case, remember that as soon as you throw that switch, the current hits a maximum. Well, the higher the frequency here, the more, think of it as a switch opening and closing, faster, 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 faster. And so you're limiting your response to like the portion of the curve where the current is the maximum. And so the higher the frequency, the more times the AC wave goes back and forth, positive and negative, the lower the capacitive reactance. The lower the frequency, the higher the capacitive reactance. Any questions? Am I confusing you so far? No? Now, in a circuit with a capacitor, Ohm's law still applies, but we don't have resistance anymore, we have capacitive reactance. So the equations are basically the same. You have I equals V over XC. All right, that would normally be I equals V over R, but you just put XC there. V equals I times XC. And XC equals V over I. So it's the same equations as the typical Ohm's law equations for resistors. You just change the resistance to capacitive reactance. And as you change the frequency and as you change the value of the capacitor, this value is going to change. So there's a variable in there. Now who has questions? Nobody. Wow. Okay, what I want to do now is actually show you, let's see if I have any calculations that I want you to do here. Not yet. I want to show you a video. I could not get the projector connected. This computer normally is connected to the overhead, but it isn't, and I wanted to access a website for you to see. So I have it pulled up on my laptop, and I want you to just watch something real quick because the analysis of RC circuits and RL circuits and RLC circuits is done using vectors. And so a vector is nothing more than a parameter that has both magnitude and direction. So I would represent a vector like this, as the length of the vector represents the magnitude and the direction represents, and this angle represents the direction, okay? And we're going to use vector analysis to analyze RC circuits. And I want you to see the relationship between a vector and an AC wave. I want you to see how that all works out. So let's look at my laptop here. If you just gather around here, and this will only take a minute or two. Okay, now what I typed in here in the search box is I typed in phasor representation. Did I spell that right? I guess. Phasor representation of sine wave. A phasor is not, it's like if you're a Star Trek fan, a phaser is a weapon, right?
Yeah.
But these are not weapons. A phaser is nothing more than a rotating vector, a vector that rotates in space. And I'm going to play this a couple times, and you can see that this vector here, which is right there, as it rotates counterclockwise, which is the conventional direction for a phaser, as it rotates, it's going to carve out a sine wave. And we'll play this a couple times so you get the visual. So there it is. Here's the vector, see it? And the projection of that vector on the vertical axis creates that sine wave. Okay, so 360 degrees there corresponds to 1 revolution. Let's play that again.
I think you can make it bigger, right?
Yeah, can't see it. Okay. Can I stop that? So what's happening is that here's the vector, right there, that angled line, and the projection of that vector onto the vertical axis, the length of the vertical portion of that vector is equal to the magnitude of the sine wave at that point. So let's play it. I'll play it one more time then, so you get an idea. Okay? And this is why we can use vector analysis to represent an AC wave. And it always wants to go to the next video, daggone it. Do it one more time. There it is. See, Russell, when you know C programming language, you can write stuff like this. Okay, are you getting it? Getting the visual?
Getting it.
Okay. Okay, so let's look at an RC circuit now. And we're going to connect that to a sinusoidal source. And I'm going to pick just an instant in time. I know that the source is changing over time constantly, but we're going to pick an instant in time and look at what happens. I know that in that resistor, for that resistor, the current and the voltage are going to be in phase. So if I have a vector here that represents the voltage, I can represent the current. Might not be the same magnitude, but I can represent the vector for the current by using an arrow in the same direction. However, when I do the same thing for the capacitor, I have to use vectors that are offset by 90 degrees. And I know that in a series circuit, the current is the same everywhere. It's the voltage that's different, okay? So I have to represent the current across that capacitor like so. Might not be well, it is the same magnitude. So let me just draw a little bit shorter. So that's the current across that capacitor. But the voltage is going to lag the current by 90 degrees. Current leads voltage, voltage lags current. So, okay, I've got my color. So the voltage across that capacitor is going to lag the current by 90 degrees. Because, and I drew it down this way because our reference direction in terms of the rotating vector, the phasor, is always counterclockwise. So this guy, IC, is always leading the voltage if you're going counterclockwise. So now I want to analyze this circuit. I want to find, let's say, the total opposition to the flow of current. Well, I really can't do anything by starting with the current. I mean, it's the same situation as we were in when we were just looking at resistors. So I have to use voltage as my starting point. But here's an interesting thing. If you draw the vector for the voltage across the resistor, it's 90 degrees out of phase with the voltage vector across the capacitor. All right? I drew them about the same length. They're not necessarily the same length. So let me just... Okay? So all I'm doing is taking this vector, putting it down here, taking the VR, the green VR, putting it there. So the total voltage in that circuit is the vector sum of those two phasors, of those two vectors. So if you look at your vector mathematics, you just use the Pythagorean theorem. And voltage, the total voltage is equal to VR squared plus VC squared. Okay? But here's what I really want you to see. Voltage, the total voltage is equal to the total current times the total impedance. Impedance is resistance plus capacitive reactance. It's the total opposition of current flow by those two components, and we use the letter Z to represent impedance. The voltage across that resistor is equal to the current across the resistor, current through the resistor times the resistor. We're squaring out everything because we're starting out with this equation here. And VC squared is equal to IC squared times XC squared. Okay? This is really of no value to us right now. This equation is really of no value to us. I'm just going to, at this point, I'm going to eliminate that. So what I've done is I've started out with my two vectors for current and voltage across the capacitor, the two vectors for current and voltage across the resistor. I know that the current is the same everywhere in a series circuit, so my starting point is going to be voltage, and because of the fact that those voltages or waveforms are out of phase by 90 degrees, well, they're out of phase by 90 degrees, I got to draw this guy, and now I want to use this equation, which is basically the Pythagorean theorem, to come up with a total impedance for that circuit. So what do I have? I have I squared, let's say that's the source voltage. So I have I squared ZT squared is equal to I squared R times R squared plus IC squared times XC squared. And I know that the current is the same everywhere, so if I just divide by current, these guys all drop out. So I squared is equal to IR squared is equal to IC squared. It's the same current. And the equation that I end up with is that the total impedance is equal to R squared plus, the total impedance squared is equal to R squared plus XC squared. The total impedance of that circuit is equal to the square root of R squared plus XC squared. Any questions? Getting it? But even though, now let's look at this phase angle. We know that the voltage is out of phase, voltage across the capacitor is out of phase with the voltage across the resistor. Currents are in phase. But what about the overall phase angle between voltage and current? Because this resistor wants to keep everything in phase. It's fighting to keep current and voltage in phase. The capacitor's fighting to keep that 90-degree offset. So the end result is going to be a relationship between current and voltage that is not quite 90 degrees, not 90 degrees, it'll be less than 90 degrees. Well, what is that? Well, here's what we're going to do. We're going to start out with, since voltage across the resistor, I'm going to make that the reference, I'm going to put an angle there. And I'm going to say, I'm going to try to find the value of that angle. So the tangent of theta, let's use a little bit of trig. Tangent of theta is opposite over the adjacent, so that the tangent of theta is VC over VR. But VC is equal to IC times XC. And VR is IR times R. I'm just pulling the equations off of here, getting rid of the squared part. And I know that current and through the capacitor and the resistor are the same, so I'm going to get rid of those guys. So the tangent of theta is XC over R. And the overall effect of these two components is going to be a phase difference between current and voltage that's going to be equal to the arctangent, or the tangent to the -1 of XC over R. That gives me the overall phase angle. If I put a meter across this capacitor, I'm gonna, current and voltage, it's gonna be out of phase by 90. Across here, in phase by, it's gonna be in phase, but if I put my meters here and span the resistor and the capacitor at the same time, I'm gonna get a phase angle that's equal to whatever the value, whatever my capacitive reactance is divided by the resistance. Take the arc tangent of that, the angle whose tangent is arc tangent, and that's the equation right there. So here are the two important equations that you want to write these down on your file cards. I lost my wheel.
Oh, no.
Oh, no. Make sure you put RC series, because when we get to parallel circuits, they're not the same equations. I want you to know. It only gets better. And I want to reinforce that here with a little exercise. Actually, two of them, before we get into parallel circuits. Now, you know when I did parallel resistors, you know the voltage is the same across all those resistors, and I actually started with the current. The current is the one that is the starting point. So I'm going to do the same thing here when we get into parallel. But let's go through an exercise. RC circuit calculations, then I have another one that right after that, I'm going to give them both to you, which involves multisim, might as well, and then we'll go through them. So there's this guy, series RC circuit, Alex. Wait, is that the same? Well, I'll get the other set. Start. Okay, here's the other half of that. So that's the second one is the multisim.
It happens, it happens. Yeah, that makes sense. No, that's not, I just sneezed. That's weird. What'd you do?
for that first one, you guys getting an angle of almost 0 degrees?
Yeah.
It's a real small angle. That resistor is dominating like crazy. Yeah. So I just want you to know you're not, if you're getting that kind of an answer, you're not wrong.
Same. Yeah. Oh.
Is anybody on number 2? Anybody get to number 2? Okay, good. Change the frequency of number 2 from 5 kilohertz to 500 kilohertz. Yeah, that'll give you a little bit better answer.
I didn't. Yeah. Ooh.
Okay, one more change. Number 2 is not working out for me at 500. Change number 2, change the resistor to 1 kilohertz from 10, and change the frequency from 5 kilohertz to 500. 500 hertz. See what that does.
You said change resistance to what?
1K. Lower the resistance to 1K.
Nice. Same.
Who's done?
I was done before you changed the number.
That's fine. I'm gonna go over these, the numbers are not working out, so we'll just, I'm getting resistors that are so dominant that the phase angles are almost zero.
2.9 thousand.
Yeah, it's crazy. It's good, it's a good exercise for the math, that's about it. Okay, before you get to this, these are, I'm gonna go over these because they could probably a little bit more frustrating than anything else. I'm just gonna go over these for the mathematics, and then you can do your multi-sim, which will be the second part, okay? So the first one, we have an RC circuit, 2.2 microfarads, and just goes to show you, I'll just wanna show you how sometimes these can be a little bit crazy. 2.2 microfarads and a 1K resistor, 60 hertz AC source. So the first thing you want to do is calculate the capacitive reactance, which is 1 over 2 pi frequency times the capacitance. So that's 6.28 times the frequency, which is 60 times 2.2 microfarads.
Yeah,
Is that what that is?
It just says regular.
2.2 farads.
Yeah.
So that is a huge capacitor. And that, I get approximately 1.2 times 10 to the minus 3 ohms. So when you have milliohms like that and you're looking at a 1K resistor, and you have this, so this is milliohms and that's a 1K resistor, well, the impedance is going to be whatever the resistor is. I mean, that capacitor is almost no effect. So you're going to have an impedance of approximately 1K, and the resistor is going to dominate so much that there's really not going to be any phase shift between voltage and current. Well, Jared, what'd you get, like 10 to the minus something degrees? It's crazy. So that's an example of where you have a resistor that just dominates the entire circuit. Now the second one, not too much better. Let's look at the second one. We have 5 microfarads, and I'm asking for the magnitude of magnitude and phase angle of the circuit. So again, XC is 1 over 2 pi FC. What did I finally change that to? 500 hertz? And 1K resistor, 1,000 ohms. Oops. 500 hertz and the capacitance is 5 microfarads. So I have this. And that comes to $6.63.7 ohms. So when I calculate the total impedance, I now have my 1K resistor squared plus 63.7 squared. Again, my resistor is going to dominate, but I don't know how much. It might not dominate quite as much in this one. Let's see what it is. I get 1,002 ohms. That phase angle's gonna be probably a couple of degrees, not much more than that. So that's the total impedance, and my phase angle is going to be the tangent to the -1 of XC over